Hey guys, Eden here. We're going to solve now a very common coding interview question. Now this question is called twosome. So basically what you need to do in this question is you get a list of integers and you get something that's called the desired sum. So it's an integer also. And you need to find in this list two elements which add up together to the sum. So for example, we can take a look on 2 and 5, they add up to 7. And we can take a look at 1 and 6, also they add up to 7, so it's also a valid solution. And 3 and 4 also add up to 7. So there are many variations for this question. A lot of people just like to ask to return a boolean, so whether there exists a twosome or not. Some people ask to return all the possible pairs, which are the twosomes, and some just ask for a valid solution. So in this tutorial, I'll just show you the version that just outputs a certain solution, or it answers that there isn't a solution. So we're going to solve this in a few ways. The first is going to be the most naive way. And the most naive way to solve this is to just iterate through all the possible pairs to see if the pair add up to the twosome. If so, to return them. So it's a very naive solution. So let's just do it quickly. And right here, we're iterating through all the pairs. So if num1 plus num2 is equal to the desired sum, we want to return num1 and num2. And if we finished iterating and we didn't return, so it means that we didn't find a twosome. So let's just test it. I'll just quickly put a snippet over here. So yeah, we'll test it with 7. Let's see. Yeah, we got 1, 6, and it works. And now this isn't a full solution because if we take, for example, the number 2, we will also return 1 and 1 because we are iterating through all the possible pairs. So we're also iterating duplicate values. So yeah, if we want to exclude it, it's not a problem. So we'll just have to handle this list not to contain this num. So we're not going to do it, but you're most welcome to do it. But this solution is also a naive solution, so it's very, very painful when we're talking about runtime complexity. So it has big O of n squared of runtime complexity, and it's the most simple solution. It works, but we can do better for this. So let's just put it aside and let's write a better solution. So we'll call it twosome better. It also takes a list and desired sum. Yeah. So what we're going to do in this solution is we're going to sort first the list. So now we have this list. It's also sorted. So let's assume we have a sorted list now. And what we want to do is we want to start from the edges of the list. So we want to start from the start and the end. So we will be doing something like this when we're iterating it. So we're going to sum the minimal element and the maximal element, because this list is sorted, so the maximal is at the end and the minimal is in the beginning. And we're going to see if it is equal to the twosome. So if it's equal to the twosome, then we're all set and we'll return the answer. If not, we'll see how we compare it with the twosome. So if, for example, our twosome is going to be, 5. So we have 1 and 7, we have the sum of 8. So 8 is bigger than 5, so we know that we have to get a lower sum. So what do we do if we need to get a lower sum? This element we were pointing on right now is the lowest already. So it's the minimal element. So we will just decrease the index of this element and we will iterate to this element. So we will take a look at this one and we'll ask the same question again. Is the sum 6 and 1 is equal to the 2 sum. No, it's 7, and 7 is bigger. So we'll go and check for a minimal solution. Vice versa, if we have something that is smaller than the 2 sum. So we will just take a step forward, and the left index would be a number which is bigger. So yeah, so maybe if we'll write the code, it will be clearer. Yeah, so we'll just make the index start, and end is going to be the length of the list, -1. Oh, forgot the equal sign. Okay, so now we're pointing to the edges of the list. So we're going to iterate through this while start is smaller than end. Yeah, so when we just get to this point, it means that we searched all possibilities and the 2 sum didn't exist. Yeah, so we'll calculate something that's called the current sum. Sorry. And it's going to be the list at the beginning and the list at the end. Okay, so now we're going to ask if the current sum is equal to the desired sum. So we found the 2 sum. So we want to return the element in the beginning and the element in the end. And now we're taking a look maybe if the solution, for example, is bigger. Okay, so if the current sum is bigger than the desired sum, so what you want to do, it's the scenario where, for example, if we have 5 here and 1 and 7 is larger than 5, so what we want to do here is we want to decrease the value. So we want to take a look at 6. So we'll just take the end index, and we want to decrement it by 1. And we want to start looping all over again and checking it. So if we have the current sum is going to be smaller than the desired sum, so it's the opposite case. So now if the current sum is smaller than the desired sum, so the desired sum in this example is going to be 9, and we're looking at 1 and 7, it means that we need to get a bigger sum. So this element is always the biggest element in the array because it's a sorted array, and 1 is the smallest. So we can just take 1 to be 2. Okay, we're just incrementing the index of the smallest element. So now we're looking at 2, and we can start iterating over the loop. So we just do start plus equals 1. Okay, so yeah. And then we return none if we didn't find, if we finish iterating through the list and we didn't find. So let's take a look now. So let's test it. Yeah, so here we are just putting 9 over here, and yeah, so we have 9 and 7, and this is the solution that we wanted. Let's just put here, for example, 7. Let's see what we get. 1 and 6, we have a big number. We don't find it. We put 2. Also, there is no solution. Notice that the solution doesn't need to check if we have duplicates or not because we're not iterating through all the pairs. So 4, yeah. Okay, so it's a valid solution. It's better than the earlier solution. Its runtime complexity is big O of n log n. So basically, it would cost us to sort this list. So it would cost us n log n in runtime, and the iteration of this list is going to be big O of n. So we eventually get for this entire function big O of n log n. So this is a better solution, but it's not the best solution. Okay, so the best solution is using hash tables. Let's just write to sum best. Now I want to say that whenever you're in a coding interview and you have a question, always think of hash tables, because a lot of tricks and a lot of questions can be solved with hash tables, and it's very safe to say that if you just think of the path of using a hash table, maybe you'll get it right. Let's talk about the hash table solution. So what you want to do is you want to build a hash table So we put everything in a hash table. Okay, so the values are just booleans. It doesn't really matter what our values are. So what we want to do is we will say, for example, we will just iterate through the list. Okay, so let's say we have this desired sum equals to be 8. So we will iterate through every element of the list. We will calculate what is the complement to the two sum. So for example, for 1 is 7. Okay. For 1 is 7, for 2 is 6, for 3 is 5, and so on, because those are the complements. And we're going to say, hey, okay, so I'm iterating through 1 now, so now I need to find whether 7 exists in our hash map. So I will check in our hash table whether 7 exists, and if it does, it means that we have the two sum, and we'll return a number and its complement. So the lookup in the hash table will cost us big O of 1, and it's very, very fast. And the entire solution would be just big O of n, which would be building the hash table, which would take us big O of n because we're iterating through the list. And the lookup and the iteration again over this table is going to be, over this list is going to be also big O of n. So this entire solution is big O of n, which is much better than the previous solutions. Yeah, so let's implement it. We'll create a hash table, create hash table, and it will take the list. Let's just do some top-down implementing. So we'll assume that we have here our hash table. So let's say we have our hash table, which is comprised of the numbers and the booleans. Okay, it doesn't really matter what we have in the hash table of the values of the keys. So let's assume here we have a hash table. Okay, so just so it won't be annoying, so let's just implement this function. So yeah, so right now we have the hash table. Okay, so we have this one over here. And what we want to do is just to iterate through every element in our list. So from num, for num in list. Okay, so we're iterating. We'll calculate the complement, so it's equal to the desired num. Here is desired sum, sorry. It's going to be the desired sum minus the number. Okay, so now what we want to do is we want to see whether we have this complement in our hash table. So we're just going to look it up. Let's say like if the complement is in our hash table keys. Okay, so it means that we have the entry of the complement. So for if we had here the desired num here was 8 and we were at 1, so the complement is 7. So we're saying, hey, does 7 exist in our keys in the of the hash table? So yes, it does exist. So if so, we want to return the num and its complement. And if not, so we want to return none. So we're going to do it for each element of this list, and then that's how we're finding very, very fast whether there is a two-sum or not. Now this will cost us eventually big O of n because we're iterating only twice. Once is to build this hash table, and the second time is this iteration. Yeah, so if we test it, keys, hash table dot keys. Oh yeah, we didn't implement it, so yeah, forgot to implement it. So yeah, now we just want to create a hash table. Created the empty hash table, and then I'm just going to iterate over the list, and I'm going to put in the hash table in the num position, for example, true, and that's how I'm filling our hash table, returning the hash table. Yeah, so we wrote it. Now let's test it. So for 4 there isn't a two-sum, but there is, so something is wrong in the implementation. Oh, we didn't return it, sorry. Okay, so I just returned it. So now we're going to return, we're going to check. Okay, forgot to put here the return. So yeah, so 1 and 3 are equal 4. Let's try 7. Also works. Let's just try 2. Now 2 is not supposed to work, but it will take us to this one. So it would say 1 and 1. So we can delete those duplicates. So we just from the keys, we're just going to not include the number. Yeah. So do something like this. So yeah. So here we don't have a twosome, and this works. So yeah, that's basically it. So we just looked on a very common coding interview question, which gets asked a lot. And we saw 3 solutions. So there was the naive, the better with the sorting, and the best one with the hash table. Now, just a coding interview tip. It's always good to start with the naive solution. It's the easiest and it's the easiest to implement. So you can just start with the naive solution and then gradually you optimize your solution. And another tip is to remember to go to hash tables. So yeah, it can help you to solve many questions. Now, something worth mentioning in a coding interview is the exact runtime analysis. Now, I remind you that in our better solution, the one with the sorting, our time complexity analysis was big O of n log n. However, this is only worse time because sorting a list with an algorithm like merge sort cost us big O of n log n worse time. Now, in our best solution, we must say that the best solution is big O of n on average. And why is that? Because retrieving an element from a hash table is big O of 1 in average. And in worst case, it can become big O of n. So the entire runtime analysis, if we're talking about worst case, in our best solution is going to be big O of n squared. So I'll say it again. If we're talking about our best solution, and we're talking about the worst case scenario, and this scenario is when we insert to the hash list, we solve the collision by adding those elements to a list. So we solve the collision with a linked list, for example, which is the most common way to implement a hash table. Then this will cost us big O of n in worst case. So our entire solution and our best solution, which uses those hash tables, is going to cost us big O of n squared. So because we're in a coding interview, it's something worth mentioning it.